Imagine a city that shrugs off natural disasters, a metropolis designed to bounce back stronger. What if the blueprints for our future urban landscapes already exist, hidden within the genius of engineering? This video will reveal how we can build cities that don't just survive, but truly thrive, no matter what tomorrow throws at them. From rising sea levels to unpredictable weather, our cities face unprecedented threats. But what if the answer isn't just reacting, but proactively building resilience into their very foundations? Discover the groundbreaking engineering solutions that are transforming vulnerable urban centers into unshakable bastions against future challenges. Unpredictable challenges in building modern cities include environmental shifts like changing weather and rising sea levels, technological disruptions that can make infrastructure obsolete, social dynamics such as unpredictable population growth and increasing inequality, logistical hurdles like delivering materials in dense areas, and governance issues such as fragmented policymaking. These factors combine to create complex situations that strain existing infrastructure, affect public health, and threaten the long-term sustainability of urban environments. Extreme weather events, rising sea levels, and other climate shifts pose unprecedented threats to urban infrastructure and safety, requiring innovative adaptation strategies. High population density, pollution, and inadequate access to green spaces and sanitation contribute to respiratory illnesses and other health issues, as highlighted during the COVID-19 pandemic. The pace of technological advancement and evolving population needs can outstrip the development of traditional infrastructure, leading to what are sometimes called mobility crises and inadequate service provision. Climate shifts, resource scarcity, and unexpected crises are interconnected global challenges that threaten human security by intensifying competition for vital resources like water and food, displacing communities, and fueling conflict. Climate change drives more frequent extreme weather events, degrading land and impacting food production, while resource depletion, exacerbated by a growing population, further strains available resources. These combined pressures act as threat multipliers, making existing political and social challenges worse and creating a cycle of poverty, migration, and instability, especially for vulnerable populations. These climate events reduce the availability of vital resources such as water and fertile land, which are already in high demand due to a growing global population. Climate change and resource scarcity don't occur in a vacuum but amplify existing challenges, acting as threat multipliers in areas already facing development or security issues. Cascading failures in urban disasters occur when the failure of one system, like power or communication, triggers failures in others, creating a disaster chain that amplifies the initial event's impact. Urban vulnerabilities like complex, interconnected infrastructures, lack of preparedness, and inadequate communication exacerbate these failures, making resilience a critical need for sustainable cities. A failure in communication systems during a disaster can hinder coordination, resource allocation, and the spread of vital information, making the overall situation worse. Extreme rainfall can lead to flooded transportation networks, overwhelming drainage systems, and causing power outages, which then disrupt communication and water supply, creating a citywide problem. The increasing complexity of urban infrastructure makes them more vulnerable to cascading failures, as a disruption in one network can quickly spread to others. Civil engineers are foundational to resilient infrastructure by designing and constructing systems that withstand disasters, incorporating sustainable and green building practices, and creating long-term plans for maintaining and adapting infrastructure. They are at the forefront of addressing challenges like climate change, urbanization, and growing populations by ensuring communities are safe, functional, and can thrive in the face of adversity. Civil engineers assess risks and design infrastructure to withstand natural hazards such as earthquakes, floods, and rising sea levels, mitigating damage and loss of life. They also play a crucial role in post-disaster recovery efforts. In essence, civil engineers are the architects of a secure and thriving future, building communities that are not just functional but also robust enough to withstand future crises and adapt to evolving environmental and societal demands. Smart grids use digital technology to improve the electricity network's efficiency, reliability, and ability to integrate renewable energy sources. Robust transportation systems rely on intelligent infrastructure, real-time data, and smart logistics to create efficient, safe, and sustainable mobility. Adaptive water systems employ advanced sensors and data analytics to monitor, manage, and optimize water distribution and usage, enhancing efficiency and conservation. An electricity network that uses digital technologies, sensors, and software to optimize power supply and demand in real time. Water management systems that use technology to adapt to changing conditions and optimize water resources. Advanced sensors, real-time monitoring of water usage and quality, and data analytics for intelligent decision-making. Efficient water distribution, enhanced conservation, early detection of issues like leaks or pollution, and increased system resilience. Adaptive transport systems significantly impact engineering by enabling real-time, data-driven optimization of complex urban mobility networks, leading to increased efficiency, reduced travel times, lower fuel consumption, improved sustainability, and enhanced urban livability. Engineers are involved in designing and integrating flexible frameworks for these systems, which utilize AI, sensors, and networks to dynamically adjust traffic flow, manage public transit, and facilitate user-centric, user-friendly multimodal transportation experiences. Engineers design systems that can adjust to real-time conditions, such as traffic congestion and accidents, to optimize traffic flow and ensure smooth movement of vehicles and pedestrians. Engineering plays a critical role in building transport systems that can adapt to shocks and stresses, such as chronic environmental issues or acute events, by providing resistance and enabling quick recovery. Modern city water systems for flood prevention use both green infrastructure, like bioswales and sponge cities that absorb rainwater, and gray infrastructure, such as dams, levees, and smart drainage systems that manage and control stormwater. The integration of these systems helps manage urban runoff, reduce flood volume, replenish groundwater, and protect cities from the increasing risks of intense rainfall and climate change. Structures designed to store stormwater, allowing it to infiltrate into the ground, which reduces the volume in drainage systems. Protecting individual buildings by elevating utilities or sealing walls to prevent water seepage. Structures designed to store stormwater, allowing it to infiltrate into the ground, which reduces the volume in drainage systems. Principles for urban nature-based solutions. Ambioecological principles inspire resilient urban systems by using nature-based solutions like permeable surfaces, urban green spaces, and integrated biodiversity to enhance adaptation to climate change, mitigate hazards, improve public health, and foster sustainability. Permeable surfaces reduce stormwater runoff and improve water quality, while urban green spaces cool the environment and provide vital habitats. Integrated biodiversity, through networks of green infrastructure, strengthens ecosystem functions, creating more adaptable and healthier cities that can withstand environmental stresses and provide benefits to both people and nature. Vegetation in green spaces intercepts rainfall, transpires water, and provides shade, which helps to regulate the urban microclimate and reduce the urban heat island effect. IoT, AI, and big data transform urban crisis response by using interconnected sensors to gather vast real-time data, which AI algorithms then analyze to identify patterns, predict potential crises, and optimize resource deployment for effective and proactive management. IoT sensors provide granular data on traffic, energy, and human movement, which feeds into big data platforms. AI analyzes these enormous datasets to detect anomalies, forecast future events, like natural disasters or public health outbreaks, and enable dynamic, informed decision-making by city officials for more resilient and livable urban environments. Employs machine learning and deep learning algorithms to process and interpret the big data, extracting meaningful insights, identifying patterns, and generating predictions and forecasts. IoT wearables and big data analytics during a pandemic like COVID-19 helped track patient health and make predictions to improve healthcare services. Hyperconnected urban environments present ethical considerations around data privacy, bias in AI, and equitable access, alongside major cybersecurity challenges like the vast attack surface of IoT devices, sophisticated attacks such as ransomware, legacy system vulnerabilities, and the risk of cascading failures across interconnected systems. Despite advanced technology, human error remains a significant factor in cybersecurity breaches, emphasizing the need for ongoing training and awareness. The growing sophistication of cyber attacks, including AI-enabled threats, ransomware, and phishing, poses a constant challenge to protect critical infrastructure. Building resilient communities globally involves megaprojects like sustainable infrastructure and policy shifts such as integrated sustainable development, which enhance urban resilience by addressing natural, economic, social, physical, and institutional dimensions of cities. Strategies focus on identifying vulnerabilities, fostering community engagement, developing emergency plans, and integrating environmental, social, and economic sustainability to help cities survive, adapt, and thrive against chronic stresses and acute shocks. To empower viewers for resilient community development, provide specific steps like joining or forming local groups, advocating for policy changes, sharing knowledge, supporting local initiatives, and building social networks. Frame community resilience as the ability to adapt and recover from shocks, emphasizing collaborative, community-centered approaches to planning and preparedness. Community resilience is a community's collective ability to withstand, adapt to, and recover from challenges like natural disasters, economic hardship, or social crises, resuming daily life effectively. Engage with local officials and advocate for policies that support community resilience and preparedness. Share information, skills, and resources with your neighbors to enhance collective preparedness. Take part in community health event planning and personal preparedness efforts to improve the community's overall readiness. Support local businesses and organizations that are contributing to sustainable community development. Foster a positive outlook and take proactive steps, even small ones, to contribute to building a more resilient community for everyone.